Hi there. Let's talk about organic chemistry. So, first of all, what is organic chemistry? Organic means that it comes from living matter. So, organic chemistry is the study of the molecules that make up living things. Um, the definition actually goes beyond living things in terms of how chemists see it. But the original definition, and the one that we're using, is that it's the study of the molecules that make us up and other organisms. Now, there are two things that are true about all organic molecules. They are all made, the backbone, the framework, is made of carbon atoms. Carbon atoms join together to make different structures, different shapes. And on those carbon atoms are other groups of atoms known as functional groups. These functional groups contain elements like hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And those come together in different ways and stick to the carbon, and that gives the molecule its unique chemical properties. So let's start by looking at carbon. So, if you remember, in terms of drawing an atom, you use the number of protons. In this case, carbon has 6 because it has the atomic number 6 to determine the number of electrons. So, the carbon atom has 6 electrons, and 2 of them go in this first shell, leaving 4 of them in the valence shell. Now, because that valence shell actually can hold 8 electrons, we say that carbon has 4 empty seats, and that means that it can form 4 bonds. And being able to form 4 bonds makes carbon a versatile building material. It can bond with 2 things using double bonds. It can bond with 4 different things. It can bond with 3 things using a single bond, 2 single bonds, and a double bond. Now, this means that carbon can form long chains and still have room for functional groups, or it can form rings of different numbers of carbons. And because these carbons can hold on to themselves as well as functional groups, there's room to add a lot of functional groups that give that molecule some chemistry. Now, drawing all of these carbons and all of the bonds can be pretty tedious. So we use a shortcut, which is that we don't draw the letter C anymore. So this chain of carbon becomes this, where at the end of each segment, we assume there is a carbon. So this is carbon, 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 carbon. And for our ring structure, same thing. Where we have 5 carbons in this ring, now we just have the 5 angles, 5 corners, and each of those corners is a carbon. This is a lot easier to draw. Now, we can still add the bonds for the functional groups doing this. So again, this chain is now this chain bent. But if I want to show that a carbon is bound to a functional group, I just add it there. Or I draw the other 2 bonds of this carbon here, and one of them's holding a functional group. And our rings would look like this. So we can show the bond and the functional group for our carbon ring. Now, let's talk a little bit about functional groups. Functional groups give the molecule its chemical properties. So the first one I want to talk about is the hydroxyl group. A hydroxyl group has this molecular formula. It's an oxygen. Oxygen always has 2 bonds, and that oxygen is bound to a hydrogen. So one of its bonds is to hydrogen, the other bond is to the carbon that forms the framework of this organic molecule. So here's a drawing of it. Here's the carbon of whatever molecule we're building. Here's the oxygen, which has a covalent bond to that carbon, and also a covalent bond to this hydrogen. Now, hydroxyl groups should kind of remind you of water. They are, in fact, polar. Just like we saw with water molecules, the electrons spend more time around the oxygen than they do the hydrogen. So there's a slight distribution of charge here. And because hydroxyl groups are polar, that means they like water, and they're going to dissolve well in water. So we say that they are hydrophilic. This means water loving. All right, the next group is called a carboxyl group. Carboxyl groups have the molecular formula COOH, and they, just like we saw with the hydroxyl groups, there is a carbon that's part of whatever molecule we're building. And this group actually contains its own carbon. This carbon is bound to 2 oxygens. This one has a double bond. This one is a single bond. So if we count the bonds, carbon still has 4. 1, 2, 3, and 4. And then this is kind of like a hydroxyl group. So similar to the hydroxyl group, this functional group is polar. There's a distribution of charge. That makes it hydrophilic, meaning that it likes water and will dissolve well in water, or cause the molecule that it's part of to dissolve well in water. But this is also acidic. Now, if you recall, acids are proton donors. When you put them in water, they tend to give up a proton, and so it is donated to the solution. The solution becomes acidic. This is the proton that gets given up in certain circumstances, in certain solutions. So this is an acid. Now, the next group is called a phosphate group. The phosphate group is H2PO4. Phosphorus is the P. You've seen the other elements here. In this case, we have a carbon. And the phosphorus is actually sort of surrounded by a bunch of oxygens. So this is a single bond, this is a single bond, this is a single bond, and this is a double bond, because phosphorus makes 5 bonds with other elements. And as you can see, this also has that OH pattern, which means that this molecule is also polar, is also hydrophilic, and similar to the carboxyl group, is also acidic. Now, phosphate groups are also very reactive. So they like to bond with things and then break the bond. And that's going to be very useful in a future topic. Next group is the amino group. Amino groups are NH2, N is nitrogen. And amino groups are basic. That means that they can take a proton out of solution. They can hold on to an extra proton. So if there's an extra proton out here, the amino group will grab onto it and become NH3 plus and act as a base. The last group that we're going to talk about is the methyl group. Methyl group is a carbon that has 3 hydrogens around it. So it also is attached to the framework of whatever our building block molecule is. But each of the other bonds is then occupied by hydrogen. Now, this is not a polar molecule. It is non-polar. There is no distribution of charge. And because of that, it doesn't like water. Water only likes things that are like water. So anything with a methyl group or lots of methyl groups is going to be hydrophobic, which means water fearing. Okay, so we have our carbon backbone or framework and the functional groups that we stick onto the carbon. And when we put those together in certain ways, we form the building blocks to make macromolecules. So the macromolecules, there are 4 types: proteins, polysaccharides, which are carbohydrates, lipids, fats and oils, and nucleic acids like DNA and RNA. So, we're going to next look at how we make the building block part, the monomer of each of these macromolecules.